So now first up, we have Dr. Thang Luong, Senior Staff Research Scientist and Senior Manager at Google DeepMind, here to walk us through large language models, otherwise known as LLMs, with a talk entitled Large Language Modeling, Past, Present, and Future. Dr. Thang Luong, the stage is yours.
Okay, good morning, everyone. Let me test the presenter first. Okay, good. All right, so welcome, everyone. Before I start, let me just say a few words. So, very glad to have everyone here. You know, in Vietnamese culture, we respect the teacher a lot. So I just want to say that, you know, I would like to thank Dr. Chris Manning, my advisor here, who come all the way from the US to come here and give me the opportunity to speak first, so I can give everyone here some basic knowledge about large language model before Chris, her, and the other speaker can talk about more exciting topics. So, yeah, thank you. So I want to tell a story about large language model, how I have spent probably a decade research in large language model. But before I start, before I go into the large part, can I just get a quick show of hands? How many people here know about language model? Just basic language model. All right, so about half and half, right? So I have some quick slides here to give some primer about language model, what it is. So language model is very simple. It's just the task of predicting the next word. Let's say you have something like the student open there. What will be the next word? It could be books, it could be laptops, exam, or mind. So it's super simple. And then, you know, we give it some probability, you know, maybe there's 30% chance we want the student gonna open their books, or 40% chance open the laptops, 20% chance open the exam, you know, maybe some people think more than, like maybe 10% open their mind, or something like that. So it's a simple, very simple task. There's no need for any human data. People can just, you know, go online, get lots of text, and then you can just train a huge model. So that's language model, basically. And you see it everywhere. So on your phone, when you type something, you will see how it suggests the next word. Or when you search on the internet, when you type a few words, what is the, it will know like the weather, the meaning of life, etc., the dark web. So it's very simple. So let me tell you my 10-year story about large language model. So a lot of these things also from the time that I was a PhD student at Stanford, so with Chris Manning. So this is the first picture. It's a long time ago, so we were giving a tutorial. We spent 4 long hours in the hotel room just to rehearse the talk. So that's the first picture. And the second picture is on the Independence Day of the US. Somehow Jeff Dean, the chief scientist of Google, Hockley, someone very famous, and we all ended up at Google because I think, you know, probably I was still single, so, you know, I can do some work, have nothing to do. So we did a lot of work in Google Translate. We create an open source software for anyone to use it. I think it looks a bit blurry, but this is Sundar you can get from this icon here. So he was tweeting about the software that I open sourced in 2017. And this is the slide from Chris during our tutorial. I hope you still remember. So you can see that the improvements that we have for neural machine translation here, the improvement within that 2 or 3 years is like equal the improvement during the past 10 to 20 years. And that was a big improvement at the time that led to the new Google Translate 2016 and 17. And let me just give you a brief idea of how language model works. So what you see here is actually lots of words here, and then they get turned into vectors of numbers. So each of these numbers will represent a word. So we have some German words here, and then it will start to translate. It will first produce the first word, the, and then we fit the next word into the protest, And it keeps going all the way until the end, so we get the whole translation. So this, to many people, actually very trivial these days. But at that time, it was actually non-trivial. At that time, Google Translate was very complicated. You need to learn how to translate phrase to phrase, word to word. It's not that simple, just going from one sentence all the way to the end, getting another sentence. So that's the start of neural machine translation. And something very interesting that we developed at that time, 2015, was called attention, meaning that we teach machine how to see the content, to understand which part is important. So, for example, if you translate from German from French into English, this graph will give an idea of which word corresponds to which word, and it will just learn those naturally. And that's that's a big improvement, a big innovation, I would say, the attention mechanism. And we developed that in 2015. One group in Montreal first started with the standard attention. We simplify and improve it to have something called dot product attention. And then that led to the transformer architecture. So this is what actually powered ChatGPT and all the large language model for technology that people have been talking about. And some people say Google invented the transformer, but OpenAI actually got a lot of benefit. So they have GPT. If you don't know what GPT stands for, it actually stands for Generative Pre-trained Transformer. So transformer is the architecture that powers a lot of these deep learning things. So open domain chatbot is the next phase in my journey. So at the time, we probably was fortunate to have the best chatbot at the time, 2020. So we built a chatbot called Meena chatbot. If you have time to read on the right side here, the chatbot was able to tell jokes. If you ask it, cows go to college, it would say, I heard that cow went to Harvard. And then you ask next, do horses ever go to Harvard? It would say, horses go to Harvard. And then it kept going. So it was kind of interesting at the time because, somehow just magically by learning from a lot of data, we was able to teach the model these behavior. And we was very close to human performance. So Meena chatbot have 79% here. Human were 86. And we was way better than Mitsuku from Microsoft and Dialog GPT. We all the best at the time. But at the time, I think probably everyone was so nervous about releasing the chatbot. Tay chatbot was a big example of saying something racist. So we didn't release that thing. But let me just give you some idea about the model. So it's actually an encoder network that tries to understand the whole content, and then a very deep network to respond in the conversation. And if GPT-2 were 1.5 billion parameters, so Meena chatbot was 2.6 billion parameters, and it's using 8 times more data. That was pretty big. But if we look through the horizon of all the models from 2018, at that time, BERT, people were saying it's very large. It have 340 million parameters. It was large. But then as we go over time, it's become too tiny. So the last one at the time before 2020 were Turing, NLG, about 17 billion parameters. But if we keep going, and it's even actually just a tiny model. And then nowadays we have GPT-3 with 175 billion parameters. We have Palm 2 from Google, 340 billion parameters. And there's some rumor that GPT-4 have 1 trillion parameters. So why large language model though? So this is the work that I did in 2022. Actually quite interesting. We tested this. This is a model that, if you give it a caption, a text, it will generate an image for you. And here we have different models, 350 million parameters, all the way to 3 billion parameters, 20 billion parameters. So what we notice is around 3 billion parameters, it can get the kangaroo, it can get the Sydney Opera House, pretty well. But if you notice carefully, it didn't get the welcome friends sidebar that it was supposed to do. And if someone notices more carefully, you will see like 3 hands, 1, 2, 3, for the 3 billion model parameters. Only until 20 billions, then we actually get a perfect image with a very nice, well-written welcome friend. So that really tells the power of large model. The more parameters, it's like mimicking our brain, like with lots of neurons. So the more parameters, the more it can learn from data, the more capable it is. And the same thing happens for language as well in terms of like translation. The x-axis is how large is the model, going from 100 million parameters to 175 billion parameters. And the y-axis is how good is the translation quality. So the more parameters we have, the better the translation it is. And in fact, this is really magical in the sense that the model wasn't really learned from translation data. They would just go onto the internet, read everything, read Reddit, read books, read Wikipedia, and somehow they were able to figure out how to do translation. So that transitions into the third part in my talk, which is about large language models. So, I told you the story, right? 2020, we have Meena chatbot, the best one in the world, but we didn't release it, and we know what's happened. 2 years later, ChatGPT came out, and it has 1 million users in 5 days. So at that time at Google, we felt like, wow, this must be like an AGI moment. If anyone ever questioned how the AGI moment would feel like. Because, before that, it took like 20 months to get 1 million users for GPT-3, 6 months for Copilot, and 2.5 months for DALL-E, which is the very famous text-to-image generation model. But for ChatGPT, it only takes like 5 days. And then many applications keep being built from ChatGPT throughout the time. So we feel very fortunate, I think probably all of us here, we're actually probably, in a moment of history, I think, that there's a nice transition. There's actually a rapid progress towards what people call, I think, artificial general intelligence, AGI. And so December, when ChatGPT was launched, there was a code red from Google. So I think Google was facing an existential threat. If we do nothing, so we're going to be perhaps left behind. So we have this a sprint of 100 days to launch Bark. It was an intense time at the time, like every week, feel like 3 weeks. And 100 days that we developed Bark feel like a year already. But luckily, we was able to launch Bark. So this is a picture with Sergey Brin, Sundar launching Bark on the 21st of March. And I was, with Quark, Etchi from our team. We were a very small team, about 40 people. And I think it's record time. I think this is the first time that Google was able to launch a product within 100 days. So I think it's quite a big milestone. So once we have launched Bark, so the next question would be, what next for a large language model? So I would say there's 3 types of problems here. Number 1 is the hallucination and factualities. So if you ask ChatGPT, when was Sam Altman's fired? I guess everyone was following the news. ChatGPT wasn't able to answer this, right? Even though it have access to the internet, it still said it was updated in April 2023. I tried Bark last night. I tried both last night. I think Bark luckily answered this correctly, with the correct details. But then it's not perfect as well. If I were to try to trick it, when was Sam Altman named CEO of Microsoft? It would say a few things, it would say it's correct that it's never been a CEO of Microsoft, but then he say he stepped down as a CEO of OpenAI, which is not correct, I think. So we call this hallucination. And I think this is actually a very important issue. If any startup can solve this issue, I think they can actually be pretty rich, I think. So we have a work this year on how to address this issue. We call it FreshLLM, meaning like how do we handle very new facts, something that happened recently, the freshness, so it's called FreshLLM. So we have a prompting technique called fresh prompt, meaning that we teach the large language model how to make better use of search result. So not just the regular search result, but also things like, the answer box, the related questions. Sometimes the related question have a correct answer, whereas the answer box, you got wrong answer for Google, actually. And we also teach the model how to do reasonings, because search result actually quite noisy. So they need to learn to find out which one is correct, which one is not correct. So what you see here is actually the kind of example that we will teach the model to do reasoning. So we will have like some search results here. The model will sort of reasoning like, Amazon never exceeded 3 trillion market cap. And then after that, it was able to answer correctly that, the market cap was around 1.9 trillion. So once we teach with those demonstrations, when the model see new example, for example, how many seats do a Republican control in the United States Senate, then it can sort of like, do the same process. It will also search the internet for evidences, and then it will try to reason itself so that it will, make good use of the correct fact from a lot of search results. So that's how we prompt the model. We call it fresh prompt. And we have a benchmark called FreshQA. This is like a data set of about 600 examples. Very new things, like, for example, I just told you, right, like when was Sam Altman fired, what is the stock price of Apple, things like that. It's changing very quickly. So we have that data set, very challenging. And when we use fresh prompt, it actually can improve GPT-4 by quite a large margin from 28.6 to 75.6% on our FreshQA data set of about 600 examples. And what we notice is that, for GPT-4 itself, there's some amount of hallucination in the way that we evaluate it. For example, if we evaluate in terms of relaxed manner, meaning that if it gets the fact correct, but it hallucinates, we still tell it to be correct. So when we have fresh prompt, it's less hallucination. So I think that's one good thing about fresh prompt. And finally, I want to talk about, superhuman reasoning. I think if you want to get into AGI, I think reasoning would be the key step to unlock. Right now, we're doing a very shallow reasoning, like if I have 4 apples, someone give me 3 apples, then how many apples I will get, which is 7. But what about math? Math, I think, would be an important milestone. I think people have been talking about IMO Grand Challenge. It's a traditional, has a long tradition from 1959. And in fact, I was a math student during high school. I almost got into IMO. I was ranked around number 8, but they only get 6 people at the top. So I was so sad, and then I stopped doing math. And then I do computer science. But I want to tell you, it's actually getting back. So the community actually quite excited about math. Hopefully next year. Someone start the funding of $10 million for anyone who can get the gold medal at IMO. Anyone can be an AI model to win the gold medal at IMO would get 10 million. So I want to share with you this work also with her on our speaker here. We made some progress in solving Olympiad geometry without any human data. So I would say it's still very hard, but this is probably a sneak peek of what we have been up to. So I just give some sense about what we're doing. So we call it alpha geometry, meaning that it's a neuro-symbolic solver. We combine neural networks to help unblock, to just derive important steps. And from that, we will let the symbolic system to carry on those mechanic steps using rules, all the rule returns. And then we do that cycle to solve a problem. Let me make it more concrete. Okay. So if you ever still remember geometry in your perhaps secondary school, when there's a problem given to you, right? Let's say they want you to prove DE is parallel to FG. If you just sit there and solve, you won't be able to solve it. And for hard problem, unless you start to draw new points and lines. So in this case, we draw new point M and N. We call this magic construction. So if you somehow figure out a way to generate or draw these extra points and lines, then you can start to make progress. So that's what we meant by magic construction. This is what the neural network will do. And then from that, the symbolic engine will just take over, apply all the normal rule, boring rule, or something like that, and then get to solve the problem. And we actually do synthetic data generation at scale. We generate all kinds of crazy diagrams, just all kinds of points, lines, circles together in an interesting ways. So then eventually you will get to interesting theorems and proof together. So there's a whole spectrum of theorem that we can get. Something very simple, with maybe one proof step, where you can prove two angles here, sum to 180 degrees, or something very complex with about 100 proof steps. So we get about 100 millions of such proof and theorem examples. And then we was able to train the model. So we make two breakthroughs here. One is with a symbolic engine. We're better than the previous state-of-the-art for symbolic engine. And then, the average IMO contestant saw about 15.2 problems. With our model, we are 25 problems. It's also approaching the gold medalist. In our data set of the most recent 30 IMO problems. So that's where we are. And I think we was lucky to solve in 2000 and 2015 all the geometry problems, meaning that we're actually quite close to bronze medal. Of course, there's still challenges. We can only solve Euclidean blend geometry. There's other things like inequality geometry we couldn't solve. So I think that's where we are. So that's also come to the end of my talk. I think in summary, I think we make a huge progress over the last decade. And I think as people, as Hưng, Thuc, and other people have said, right, it's exciting time, there are lots of opportunities. But I think there are also a lot of challenges. I think how do we solve hallucination will be very important in the world, right? Misinformation and things like that. And then also the problem of weak reasoning, how do we do deep reasoning, etc. So with that, thank you.
Thank you very much, Dr. Thang Luong, for your valuable insights, and your talk has really given us a deeper understanding of the past, the present, and the future of LLMs.